it into little tiny cubes. And each of those little infinitesimal cubes has as its measures dx, dy, dz. Dx, dy, dz is that little cube inside that bigger one. And you're taking that, the volume of that is dx, dy, dz. Or you could say it dz, dy, dx, or you could say it dy, dx, dz, or dy, dz, dx, or dz, dy, dx, right? And that means that when you set up this triple integral, if you go from a to b, that's your restriction on x, right? So your outer integral is with respect to x. Then the middle integral, if it goes from c to d, and that's your restriction on y, then dy is your next variable in. And then the inner integral goes from r to s, that's your restriction on z, so you have dz here. So when we were doing rectangles in double integrals, could we change the order of integration? With rectangles, could we change the order? Yeah. We could, right? That's what I'm kind of getting at here. We could, if we wanted to, set this integral up and go from r to s, then c to d, and a to b of the function of three variables. And then I would have to do what? dx, dy, dz, because your rs is on the outside, so z is the outside variable. Middle variable, or the inner variable, no, middle is this one, and then the inner one is x. That's why I say here there are 5 other possible integrals. You could do this one, and then you could do dx, dz, dy, and that's only true when you have all your variables stuck between constants. You can only switch it around when you have it stuck between constants. I'm just trying to show you that it's that there are 5 possibilities. As opposed to with the double integral, there was only 2, right? There were only 2 variables, so you could only really switch the 2. When you have 3, there's 6 possibilities. This one and 5 others. Can you imagine with 4 variables, right? What would you have? What is that? What would it be? If you had 4 variables, how many different possible quadruple integrals could you have?
8.
8? Would it be 8? 24? What do you think it is?
4 times 3 times 2.
You think it's 4 times 3 times 2, so like 4 factorial? Yeah, it's factorial, unfortunately. Yeah. Because what you're doing is you're saying, like, if I have just x and y, how many different ways can I rearrange those? So you go like this. If I have 2 letters to choose from in two positions, how many ways can I choose that first one? How many are there to choose from? I have 2, but then there's only one way to do that, right? So 2 times 1 is 2. But if I have 3 variables, x, y, z, then I'm going to put them in an order, 1, 2, 3. I can choose this one. I can choose any of those 3. Then the next one is any of the 2 that remain, and then the last one has to be only 1. 3 times 2 times 1, that's 6. And then if you have x, y, z, and some other variable, let's say t, then there's 4 to choose from. So you're going to get 4 times 3 times 2 times 1, that's 24. So there would be 24 quadruple integrals, different ways that you could do it, if x, y, z, and t were all stuck between constants. You could switch the order. Yeah, we're not doing quadruple integrals. Because we're just scratching the surface here with triples. All right, so how would we do this right here? Evaluate this triple integral over e. So look, you see the function here? This is the function f of x, y, z. You can't see it. You can't visualize it. It's out there. You can try. But it's out there, right? Your input into that function is something in a point in 3-dimensional space. Now, see this notation? 0, 2, crossed 1, 2, crossed 0, 1. When you see it written like that, you are to assume that means x, y, and z. So I'm just going to go in that order. Restrictions on x, 0 to 2. Restrictions on y, 1 to 2. Restrictions on z, 0 to 1. What am I integrating? X squared yz. What's the order of integration here? dz, dy, dx. Okay, I'm going to work through this one because it's our first triple.
Can the theorem still be applied where you can separate the variables into different integrals?
Ah, very good question. Does that theorem apply where if these are separated by multiplication like this, that we can separate them into individual? The answer is yes. Now, I'm going to do this one just straight up the way it is. So here's how I would do this. I would do 0, 2, 1, 2, and then I'm about to integrate this with respect to what? Z. So that is 1/2 x squared y. I'm evaluating from z equals 0 to z equals 1. So you see why it's
Z squared.
whoa, 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 whoa. Yeah, I forgot it. Okay. I must have, well, I started it, right?
Yeah.
Okay. X squared y z squared. There we go. I think I started doing integration and then I differentiated or something. I don't know. My brain misfired there. All right, so I'm going to go 1 in here. Now, see, I'm keeping track. Z is the thing that's getting replaced. That's why I'm putting z as 1, z as 0 here. And then when I'm done with that, I'm going to go dy dx equals. Now, integral again. We don't worry about, paper and, this. Don't worry about taking up all that space on your page. It's okay. There's plenty of paper, plenty of trees. Earth's going to be fine. Z is 1, goes in here, and when I plug that in, I get something, right? When I plug in 0, it goes away. So all I really have is 1/2 x squared y, right? That's what I get when I plug in z as 1. Then dy dx. And what's next? Integrate with respect to y. So integral 0 to 2. Okay, when we integrate that with respect to y, I'm going to get another 1/2 y squared. So the 1/2 comes out, and I hit 1/4 x squared y squared. Don't screw that up. And then y equals 1 to y equals 2. And then once I figure that out, dx. When we plug in 2 for y, well, I guess we're going to get something, aren't we? So this becomes integral 0 to 2. And then, all right, let's plug in 2. 2 for y, get 4, 1/4 of 4, it's gone. So I just get x squared there. Minus, when I plug in 1 for y, I get 1/4 x squared. Y'all agree? Any questions? 2 squared 4 times 1/4 is x squared. 1/4 x squared. Subtract. Yeah. What? That's just 3/4 x squared, isn't it? That is? I'm going to pull the 3/4 out. We could have pulled that constant out a long time ago, but I just kept it in here. And now integrate, we'll get 3/4 times 1/3 x cubed, and I'm evaluating from x is 0 to x is 2. What is it?
8/3. That gives you 2.
Yeah, and we have the 3/4 out there too, so
Yeah, so it's 8.
just 2? This should just be 2. That's how we do a triple integral over a rectangle. These are fairly easy because numbers are going in the whole time, nothing gets messy. Any questions? All right. Triple integrals over a region. What if all I tell you is that the region I'm integrating over is no longer a box, okay? But what I can tell you about this region is that its shadow on the ground is type 1. So you got some region here that I'm hiding from you right now. Some three-dimensional solid up here that when you cast its shadow onto the ground, on the ground, the x's are between two constants. This is my x-axis, this is my y-axis, my z-axis. My y's are between two functions of x. So I've got g1 of x, g2 of x. That's a type 1 region. The shadow is type 1. Yes? Now, the actual region, here it is. There we go. Okay? I'll give you a whole full 360 view of this thing. So when you look at this, do you see that the z values are stuck between two surfaces, right? There's a surface on top and there's a surface on the bottom. That used to be like f of x, y, and g of x, y, right? But now these are restrictions on my z variable. They are not part of the function. The function takes stuff out of here and does stuff with it. This is our region, our domain. So what we do is we label those restrictions as the lower part of this solid is u1 of xy. That's a surface. Instead of like g of xy, u1 of xy. And then the top surface is u2 of xy. Surfaces have to have two variables go in, right? Yes? Then the curves on the ground are functions of one variable. And then the x is just constants. So your x's are between two constants, your y's are between two functions of x, and your z's are between two functions of x and y.
So I got a question.
Yeah.
Instead of like a triple integral, would we do the double integral of the domain first on the ground, and then do the integral of the u1 and u2, or would you do u2, u1 first?
You have to do u1, u2 first.
And
Then you do the double. So here's what it looks like. When you have a region that looks like that, here, that's maybe too big. Here's what your triple integral looks like. So in this case, that your x's are between two constants. Your y values are between two functions of x. So this part of it's like a type 1 on the ground. The shadow is type 1. And then your z values are stuck between two surfaces, surface u1 and surface u2. Then when you're trying to do your triple integral over that region, that solid E, of the function f of x, y, z, which you don't even know what it looks like, it's sitting somewhere else, with respect to volume, your outer integral has to be with respect to x, the middle integrals with respect to y, and your inside integrals with respect to z, and you cannot change that order. That means you've got to go do this one first. And that one, look at your limits of integration. They're going to be functions of two variables instead of here functions of one.
Pretty much what you're trying to do is eliminate a variable at each step.
Yeah, each step you get rid of one variable. Yep. All right, I'm going to move on. So here's an example. Evaluate the triple integral over the solid E of y. So look at our function, very simple function, right? Just y. That's it. And we're doing that with respect to volume, where E is bounded by these planes. X equals 0, y equals 0, z equals 0. And then 2x plus 2y plus z equals 4. All four of these are planes, right? X is 0 is the YZ plane. Y equals 0 is the XZ plane. Z equals 0 is the XY plane, right? So we're basically looking at all the coordinate planes and then this thing, which is again is another plane and it has some sort of tilt to it, right? What's the direction of the normal vector of that plane? 2, 2, 1, right? Okay. So here we go. Let me try and draw this. I've had bad luck drawing planes in three-dimensional space before, so I'm going to do my x, y, z like that. Let me figure out where this plane hits my z-axis. 4? And we're getting that by just plugging in x and y are 0, you get z is 4. Where does it hit the x-axis? 2. And where does it hit the y-axis? 2. And so we've got this little plane here. Like that, right? That's my plane. And then I have the XY plane, the YZ plane, and the XZ plane all creating boundaries. So we have this solid like this. That is E. That's E right there. Do y'all see it? The three-dimensional solid? All right. Let's try and figure out what the shadow of this on the ground looks like. Well, what's the shadow on the ground? I'm going to draw it this way. Here's X, here's Y.
0 to 2.
So 2 here, 2 here. I'm trying to draw this piece right here, right, on the ground. But I kind of turned it because I'm looking from the top. I turned it and I have this line connecting these like this. Do we know the equation of that line? What is it? Y equals negative x plus 2. That's right, because it has a y-intercept of 2 and a slope of negative 1. Agree? Okay. And so the shadow of that E onto the ground is a type 1 region, isn't it? Yes. This is type 1. If it's type 1, what's the restriction on X? What's the restriction on Y? 0 to 2, and then 0, that's the bottom, and then the top is negative x plus 2, right? Because it's the function that's dictating my y values. So this right here is stuff we've done. Now we have the one additional element, and that's we've got to figure out back here on this picture what the top surface and the bottom surface are of that solid. So if you were to look straight down on this, what would be the top of it? That plane, right? That plane equation. There's the plane equation. What would you need to do with it? Solve for z, so you can look at it as a function of x and y. So this top one right here, that's what we call u2 of xy. And that is this solve for z, which is 4 minus 2x minus 2y. Now what's the bottom surface? That's just the xy plane, the floor, right? That's the bottom of this. So the bottom of that is u1 of xy, which is just 0. Are we good? Sure? All right, I think at this point I'm ready to set up this triple integral. All right, here it comes. The triple integral will be triple integral over the region E of y dv will be the integral from 0 to 2, that's my restrictions on x, integral 0 to negative x plus 2, those are my restrictions on y, integral 0 to 2 minus 2x minus 2y. 4, thank you. 4 minus, that's this one. 0 was the bottom surface. There's the top surface. What am I integrating? Y d z d y dx. That's our setup. Pardon? Yeah, because the original function, right? The original function had y. All right, we're going to do this right now. What's the antiderivative of y? With respect to z, it's yz, right? Not 1/2 y squared. So we have integral 0 to 2, integral 0 to negative x plus 2. When we integrated that, we got yz, and we're evaluating that. Be real careful here. We're evaluating that where? Z equals the bottom, 0, to z equals 4 minus 2x minus 2y. Yes, you have to plug that in for z, and then dy dx. The good news, when you plug in z is 0 into here, it's gone, right? So all you really have to do is plug this in for z, and that's what's going to be the new integral. So if I take this and plug it in for z, a y is going to distribute to each of these. So I'm going to go ahead and write down my new integral. I have integral 0 to 2, integral 0 to negative x plus 2, and then 4y minus 2xy minus 2y squared. Good. All of that dy dx. And now we're back to a double integral, right? This is back to a double. So we've done double integrals. You could take this the rest of the way. Okay.
Something like that, you can take them individually still.
What do you mean individually?
Like you can, since it's linear, you can do the integral, or take the double integral, apply it to the 4y, take the double integral, apply
Oh, you could split this up and do double integral on this, double integral on that. Double, yes, you could, but I think that would be more work than
No,
you'd be
no,
writing down a lot more integral
Yeah, no, I'm just
signs.
saying
You could, yes, because they are separated by addition and subtraction. I thought you were saying you could split them up like that theorem. You can't do that because the x and y are, well, you could do it here. Yeah, but you couldn't, well, yeah. It just seems like too much work to me to try to do anything other than just integrate that with respect to y right now. You know,
No, it just take two. It'd just be a long process.
whatever floats your boat.
Usually buoyancy.
Okay, I'm not going to continue this one. Let's just see what the next one looks like, or the next thing, the next note looks like here. All right, well, if you can have the shadow of your solid cast a type 1 region on the ground, what if it casts a type 2 region where your y's are between two constants? Your x's are between two functions of y. And your region up here, your solid, is still between a u1 of xy, a u2 of xy. So the only thing that's changing here is the ground. What if the ground shadow looks different? What do you think is going to happen to the integral? The outers are going to switch, okay? That's all that's going to happen. So when you look at this, your outer one always has to have the constants on it. And if y is between the constants, then y becomes the outer one. The middle one is your x variable, so it's your functions of y. And then your inner integral is your surfaces. Pardon? Yes, that is a typo. This is supposed to say f of x, y, z. Thank you. I've had these notes for I don't know how long now, and I still find typos, or students still find typos. All right. Don't think I have an example for this. This is not, I mean, this is an example, but it's not an example of what I just showed you. This is just to get you to think a little bit. Evaluate where this triple integral. So what's the function of x, y, z that we're integrating? xz, okay? We're going to integrate that function. Here, the points we're plugging in live in this solid tetrahedron with these vertices. Now this should be relatively easy to draw. Let's see, 0, 0 is there, yay, I got that. 1, 0, 0, sorry, 0, 1, 0, here's x, here's y, here's z. So there's 0, 0, 0, 1, 0 is here, 1, 1, 0, out 1, over 1, right there. And then 0, 1, 1, which is up here. Can you all see this solid tetrahedron? Let's connect some dots here. Do you all see it? What does the shadow of that onto the ground look like? If I were to draw it like this, in x and y, I have a point here, here, and here, right? And it goes like this. That could be a type 1. I could do that problem type 1, couldn't I? Could I do it type 2? I could do it type 2 also. I'm going to do this one type 2. I'm just going to set it up. I'm not going to do it. I'm just going to do it type 2 just to see the difference, right? Is that okay with you? If I do this type 2, if I want to do this as a type 2, then what are my restrictions on y? It goes from where to where? 0 to 1. Now my restrictions on x are between two functions of y. So this goes from 0 to 1, but my x is between what?
Y.
This 0, and then this right here, if I take that equation, which is y equals x, and I solve it for x, I get x is y, which means this is y. Now, something more challenging. What do I have to do now? I need to get my restrictions on z, right? So when you look at this tetrahedron, what's the top and what's the bottom?
The top is 1.
The top is what?
1.
The z values change, don't they? If you move to a different point in here, the height is going to be right, different, depending on where you are in that region. Depending on where you are in here, your height changes, right? Because you're going to be on that slanted part. So let's talk about the bottom. What about the bottom of z? How about this bottom piece here? u1 of xy is what? 0. It's just 0. It's just flat on the bottom. The u2 of z, of xy, sorry, the u2 that dictates the z upper limit is actually that plane, isn't it? It's the plane right there.
So we would take the 3 points.
You take the 3 points,
Yeah.
you create vectors, you cross them, you get the normal, you create the equation of the plane, right? That we did a long time ago. That's what you would have to do. So generate 2 vectors on this plane, cross them to get your normal, use any point, then you have your equation. Once you do that, you solve that equation for z, and that will give you this up here. Right? No, I'm not going to do it. But that's what you would do, right? That's what you would do.
Is that like a mini exam question?
No, that's straight out of the book. Yeah. Understand what would be required here? Okay, now what would the setup of this integral look like? It would go 0 to 1, right? And then dy is the outside. Then it would be 0 to y, and then dx would be next. And then the next one would be 0 to, I don't know, you got to go do that work, right? And get that equation. And then I'm integrating what? xz with respect to z. So I go z, then x, then y, because the ground, we looked at it as a type 2 instead of a type 1. If you did this as a type 1, would it save you at all from doing this? You still have to do that, right? So there's no value in doing type 1 or type 2 there. All right. What about a triple integral over region E? Imagine now, instead of us casting a shadow onto the xy plane, we cast it upon the yz plane. Oh, oops, I left my code open there, sorry. Go away. Oh, wait, I have to select it, sorry. Okay. So, now your solid is out here in three-dimensional space. If you cast its shadow onto the yz plane, not the xy plane, not the ground, but this wall, then on that wall, you get a region where your y's are between two constants, your z's are between two functions of y, and your x's are two surfaces, but they're functions of y and z instead of x and y.
Would you just consider that region a type 1 region?
This would be a type 1 region, but it's on a different wall, isn't
Or
it?
Like you treat it as a type
Just like it,
1,
yep.
and then-
So look, the thing is, with this solid right here, look, with this solid, what is this? I don't remember what this is. Shadow? Oh, if you just look at the shadow. Oh, that's looking at it from the top. Look, if I pop it out of here, see? Like that. Right? That's what it looks like. But here's the problem. You cannot do this looking at it from the top anymore and going back and doing what we've been doing because if we try to, you cannot say that this top surface and bottom surface are two different surfaces. They're the same surface. And so what I'm getting at is there's no way around it other than to cast the shadow on a different plane. So that's what you would have. And then this region over here is kind of like a type 1. Y is between constants, z's is between two functions of y, right? We could also have this shadow be where your z's are between two constants and your y's are between two functions of z. And then you could also cast the shadow onto the other wall, xz plane. So basically we just have like 6 different integrals, triple integrals that I just kind of illustrated. So this is the problem we just did, isn't it? Isn't that the same one we just did? But I ask you to take it and use, instead of doing it where we are looking at the shadow on the ground, look at the shadow on the YZ plane and then on the XZ plane. I've got 5 minutes. Let me see if I can do one of these. I'll remind you of what that region looked like, although I've forgotten. So here, here, out one, over one like that, and up one like that. It was this. That was our region, right? Okay, X, Y, Z. Let's do this one. If we go onto the YZ plane, what does my domain look like on the YZ plane? YZ.
0, 0.
I go here, 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 it looks like this, right? Yes? Okay, I can look at this as kind of like a type 1 region. What's stuck between constants? Y is between 0 and 1. And then my z's are between 0 and, hold on, 0 and this right here, which is z is equal to y. It's the identity function, but see, we're not using x and y, we're using y and z. So this is z equals y, so z goes between 0 and y. Does that make sense? Okay, now you need the surfaces that are bounding this. So that's still this plane, isn't it? That's going to be my u2. What about the backside that's right up against the yz plane? What is that? u1, and what is it? What is u1? That's the easier one. It's 0, isn't it? But it's u1 of what two variables?
X. Y and Z.
yz. It's of yz. And it's 0. Now what about this one? u2, which is this plane, is yz, and that is, we don't know yet, right? You would have to take the vectors, cross them normal, and you get that plane equation and solve it for x. Because you want that equation to depend on y and z, so you solve it for x. You plug that in here. Got it? Right. I'm leaving you with quite a bit of work to do. What would be the difference on the xz plane? Now we're shooting our shadow that way. So what would that shadow look like on the xz plane? Imagine you project this point over to the xz plane. You would be here, right? This one would come up here. And where would this entire line go to? The diagonal connecting those two? That would be it. And so your x would be between 0 and 1. Your z would be between what? 0 and negative x plus 1. Y-intercept 1, slope negative 1. And then what about your surface? Ooh, this surface is a little different. I better do this in a different color. If we were looking at this surface, that would be the U2, wouldn't it? And then the U1 would be this one. I know I'm moving faster that. It's only because I have a minute left.
So would you have to calculate 2 planes?
No, this plane right here, U2, what is that plane? It's not 0. Hold on.
What's the equation of a plane?
It's the equation. What is the equation of that plane right there? U2.
The two vectors.
It's 1. What is 1 though? Y is 1. That plane right there is y is 1. So your z would, I mean not your z, your y would be bounded between 1, which is this plane, and then this plane, the u1, is that plane that you have to cross and get solved for y. I like these problems. We haven't finished them, but I would highly recommend that you do example 3, finish out example 3 and example 4 on your own time. All right, I'm going to let's stay till 1. There's a few more things that I need to do. No, I'm kidding. Y'all have a good weekend.
Do we have any homework for 12.4?
Pardon?
He said he was going to email it to us.
Yeah, there's homework. I'm pretty sure there's homework at the end of that. There's the homework for that section. There's a few more things to do in there, but you can at least get started on that. And I will send you an email on the homework for 12.1. What?
We did 12.4 and 12.5.
Say again?
That was last week. I mean, last class.
I put that up last class? Oh, wait, hold on. Did I close it? Hold on, I closed it. Oops. Where is it? 12.5, right? There we go. That's 12.5 somewhere. All right. Was anyone coming by today for office hours? I have limited availability today. We had a faculty member get sick and I might have to sub today.
So with something like a sphere,
Yeah.
triple integral, like if the sphere is centered at origin, we can split it up into 8 regions and then kind of just break it up that way.
You mean if your solid is like a ball instead of something like this, we go to a different coordinate system because it's too hard to work with in Cartesian.
That's what I mean, like, since it's, if it's centered at origin, can't we break it up into 8?
You could.
And then solve it that way and multiply by 8?
You could.
But if it's
Well, no,
not-
you can't multiply by 8. Unless your function that you're integrating is symmetric. You don't know that. So you would actually have to do all 8.
And
So-
then if it's not centered at origin, then we have to go to polar for all 3?
No, what we'll do for sphere, we'll go to spherical coordinates, which we haven't talked about.
Okay. But
And
we're
then,
gonna get there?
yes.
Okay.
So 12.5 is triple integrals, and then 12.6 is triple integrals in cylindrical coordinates, and then 12.7 is in spherical coordinates. Yeah, so we have, basically cylindrical coordinates is the equivalent to polar in 3D. And then spherical is totally different. It's just because we live on a sphere and see spheres everywhere, we needed a coordinate system for that, and it makes the
And I'm
integrals
assuming
a lot
we're gonna
easier.
calculate the center mass of a sphere.
We won't do that, but you could do it for some object that would be more interesting.
Okay.
Yeah.
You function.
I mean, you could do it to verify, right? You could. Yes, ma'am.
That's what I did. I brought this with me.
Oh, yeah.
I promise
Okay.
this was not done on.
I don't know about that. That's fine. So are you going to work that one again or no? Okay. Okay. All right. Sounds good.
Would you
Yes,
happen
sir.
to know what the homework problems are, or you don't have them?
I don't have the book. I would have just told you. Do you ever watch the videos for the homework at all?
Yeah.
Okay. If you watch the videos, it'll probably show like what problems, I'll put like number 2, then you can do that. But I'll go look at the book and see.
It's all right.
Yeah, sorry, I just don't have them with me.
I just wanted to do them like right after.
I'll do it right now. I'll go down there right now and I'll email right now. I won't wait. Okay, no problem. Have a good one. You have my cell phone number? It's on the syllabus.
Yeah.
Okay, if for some reason the email's not there in the next 20 minutes,